Our next talk will be given by Francis Moll. He has a BSc from the University of Waterloo, graduating in 2001. He has been employed in the minerals exploration industry for the past 17 years, first with Santo Geophysics, and subsequently with a group of junior mineral exploration companies. For the past 4 years, he's been working with Condor Consulting and their office in Vancouver, British Columbia. The title of his talk is Geophysical Results over the Santo Domingo IOCG Deposit, Region 3, Chile.
Is there a laser pointer on this one, Ken? Or is it just one of them? There. Oh, that's the laser pointer. Okay, so two-handed. All right. Thanks, everybody. I'd like to point out first there's an error in the program. They fixed it on the abstract section, but in the schedule it says that I work for Capstone Mining, which is incorrect. I'm employed by Ken's company, Capstone. Condor. There you go. I made it even worse. Okay, here we go. All right, brief outline. So I'll just go over the location of the Santo Domingo project, the geology and mineralization, a brief overview of the exploration history, and then the part where we really became involved in the project, which was some airborne work in 2013, and comparison with that between that airborne work and some historical ground geophysical survey work. So we're in, as Ken said, Region 3, Chile. It's the Atacama. The Santo Domingo project is located just south of the town of Diego de Almagro. It's about 110 kilometers north of Copiapó. And we're fairly close to the coast. It's in the coastal Cordillera, an area which is dominated by the Atacama Fault System, which is in the central panel as AFS. There's a number of iron oxide, copper gold, and iron oxide apatite deposits in the area which are structurally controlled by the Atacama Fault System. And these are known as the Chilean Iron Belt. It extends south of the map. That's why my box is running off. Santo Domingo project is about 30 kilometers to the east of the major Monteverde mine, and it's, I think, 130 kilometers, 120 I have there, north of Candelaria. Okay, so looking at the satellite image, the photo on the right is taken from behind the town of Diego. It's indicated by the red arrow on the overhead view. So you can see the project contains 4 named deposits. We've got Estrelita, which is dominantly a hematite iron oxide, and then we've got Iris Norte, Iris, and Santo Domingo Sur. Santo Domingo Sur and Iris are contiguous. The resource is defined over Santo Domingo Sur, Iris, and Iris Norte, and it's a little under 400,000 million tons. 0.3 copper, 0.04 gold, and significantly almost 30% iron as magnetite. As you can see in the photo from behind Diego, there's some significant elevation contrast between the valleys and the upland areas where the deposits are located. So it's about 500 meters. And in the valley, we've got significant alluvium and fluvial channels, which are blanket the bedrocks. There's really very little outcrop outside the highland areas. So looking at the regional geology, we've got the Monteverde deposit on the extreme left of the slide and the Santo Domingo area on the right. The major thing when I look at the geology map is that almost half the area is covered by alluvium. So we've got, beyond that, we've got mapped early Cretaceous volcanics of the La Negra and Punta del Cobre formations. And these were deposited in a inter-arc basin, roughly contemporaneously with sedimentary limestones. So we see that in the Santo Domingo area, the blue unit. Then they were followed by mid-Cretaceous intrusions and roughly simultaneous development of the Atacama Fault System. So you can see that Monteverde is directly on a fault. It's listed as the Monteverde Fault, which is a branch of the Atacama Fault System. Looking at the property geology, again, majority of the area is mapped as is unmapped, and that's covered by alluvium. The major units shown are volcanics. So the green is andesite, breccias and flows. And the really important unit is the orange one, which is volcanic clastic and tuffs. And then the blue is limestone. And so these were then intruded by the diorite plugs, and there's associated skarn and iron mantos. If you look at the section from A1 to A2, there's a gentle dip on the host rocks about 15 degrees to the northwest. That important orange unit, which has been intruded by a diorite sill, is sandwiched between the less permeable limestone and andesite volcanics. If you look at a close-up of the Santo Domingo Sur deposit, which is in the center, there's important structural controls due to faulting. So it's truncated on the south and southwest and on the east side. Inside the deposit, along that same section, there's some zonation of the iron oxides. In the core of the deposit, there's dominantly magnetite. In the rim, hematite is more common. You can see a core section photo on the right with hematite, magnetite, and then pyrite as iron sulfides, and chalcopyrite, which is the real target here. The mantos are massive iron, over 50% iron minerals, up to 20 meters thick. And there's a distribution of the copper minerals dominantly in with the hematite and pyrite in with the magnetite. So we have a copper-rich rim and a copper-poor core. So I had a more complicated physical property slide, but I thought it was going to get me in trouble. So I've just sort of put a blanket statement in there saying that the host rocks have really highly variable physical properties. We've got variable composition, importantly, variable porosity. And then everything has been altered in proximity to the intrusions, and there's significant weathering depth. So even where we've got a single lithology, we see significant variations in the geophysical response, which I assume are due to variations in the physical properties. The deposit contains a massive amount of iron, and both magnetite and hematite have over 5 grams per cc density, so there should be a significant density contrast. To the host rocks, there's very little actual physical property data from the deposit that I had access to. But in the Santo Domingo Sur area, they did take some core samples and do remnant analysis. There was a very strong remnant magnetism, the Königsberger ratio of 10, and the orientation was roughly opposite the current field. It's important to note that the susceptibility variation between magnetite and hematite, you would hope, would allow us to map that zonation in the deposit. The susceptibility of specular hematite is relatively low. Susceptibility of magnetite is very high. Also, we've got anecdotal evidence that there's continuity along the core. We had a geologist just place electrodes in the sulfides in the massive part of the core and see that there was continuity. If we take these massive iron, massive magnetite, and we add a small amount of chalcopyrite, some literature indicates that we have a decrease in galvanic resistivity. If we have very large proportions of magnetite, and we end up with a modest conductor, adding a bit of sulfides to that, we should have perhaps a improvement in the inductive conductivity. So brief exploration history. The project, the field work on the project began in 2002 with a regional airborne geophysical campaign. This was carried out under Far West Mining and BHP. The project was carried on after 2004, or during 2004 by Far West, and they made a discovery hole at Santo Domingo Sur in 2005. And that's really the end of the story as far as geophysics playing a role in discovery of the deposit and the exploration. They did some ground TEM in 2007, some ground mag in 2010, and after Capstone and Korea Resources took over the project in 2011, there was a subsequent airborne campaign with VTEM and ZTEM. So, with the Falcon survey, this has been trumped as one of the successes of the Falcon system. It was one of the very early surveys using the second system that they built. Coincidentally, I was involved in this one, not in flying Block 4, where the Discovery sits, but some of the other blocks. And it was kind of fun to come back to it more than a decade later. The images I show on the left of the total magnetic intensity reduced to pole and the vertical gravity gradient, they don't have any color bars. These were taken from public documents that were previously shown in 2013. In the upper right, you see target area 4A, which is where the Santo Domingo project sits. This target area was selected based on the interpretation by BHP Billiton as a gravity high response and an anomalous potassium thorium ratio. It's one of a large number of targets that they selected for follow-up. And the story really carries on from here as one of using this regional data on a property scale and doing good prospecting work. Taking the data from that survey, trimmed to Capstone's property boundaries, I found that the target areas selected matched very well to the vertical gravity gradient contours. So sub-targets were selected, 4A1, 4A2, 4A3. These were defined really well by the 25 ETVUS contour on the gravity. And so these target areas followed the project through for quite a distance, and it really was, the gravity was at the core of the discovery in that way. We can see that there's a pretty good correlation between the gravity, vertical gravity gradient on the top and the existing, or the known Iron-Ox, IOCG, mantos, and breccias. These are the stars and X's. And there's also, there's a fair amount of prospecting carried out in the 4A3 area. It was deemed promising. Some ground DCIP was carried out, and hole 3 was drilled close to the Iris Norte deposit. And this yielded 0.3 copper over 200 meters. In 2005, a further hole was collared in the proximal to the gravity high at the south of the Santo Domingo Sur deposit, and it was really targeting that northwest cutting fault, coincident with the gravity high, and they made the discovery hole at that point. It's 56 meters of 0.8 copper and 22 meters of 0.7. There's a reasonable correlation between the gravity, magnetics, and the geology here. You can see these are the iron oxide mantos that have been mapped. This is the area of the diorite intrusion. These are the areas of the limestone. So we see that fault between the limestone and the volcanics pretty well defined. And there's probably a better correlation between the gravity and the faults, excepting along the east-west area. Pull up the laser pointer. Here, this is what they call the Santo Domingo fault. And it's really quite well defined in the magnetics, but there isn't it's not so well defined in the gravity. So, a combination of the regional gravity and magnetics carried the project to the point of drilling these initial holes. So leaping forward to 2013, we had access to the project as a test bed for flying VTEM and ZTEM. These are the VTEM results. The survey was oriented lines at 130 degrees, separated by 200 meters. They were able to fly much, much lower than the Falcon system was because it was helicopter-based. And so what we see is that the late-time EM is really dominated by those alluvial materials. It's got a very high conductance. The upland areas are generally very resistive, excepting the area of the Santo Domingo Sur Iris Norte deposits. Estrelita doesn't really have a significant contrast in these data. If you look at the time constant, or add tau, on the bottom plot, there's a excellent isolation of the deposits. We really don't see a great correlation with the major known geological features. There's definitely a response in the south around the diorite intrusions, but really we're doing an excellent job of isolating the deposits and not really seeing much else with the VTEM data. Didn't point out in the previous slide, but there is a fair amount of noise from a power line running along the highway just to the northwest of the deposit. It's more evident in the ZTEM data, and we had to truncate the survey a little bit on the northeast in order to avoid getting too close to the power lines. With the ZTEM data, looking at a relatively low frequency, I think they started at 25 hertz here and went up to 600. There is definitely a correlation between the deposit locations and the total phase response and the total divergence, but we're also seeing a whole lot more. I think we're getting a better correlation with the known IOCGs, with the known mantos, and with the defined faults. I'm going to speed up a bit so I don't run out of time. We inverted both the VTEM and the ZTEM data. In the case of the ZTEM, it does a much better job of isolating the deposits. We lose some of the detail of the lithological contacts, but we're getting a product somewhat similar to what we had from the VTEM. If you look at the central panel, I've got the VTEM profiles on the top. This is a nicely isolated single peak response. Dip is indicated to the northwest. You can see a good correlation between the conductive zone and the drilling. We have the tippers from the ZTEM in the center of the stacked profiles, indicating a conductive response, and similarly a good correlation between the inverted recovered conductivity from the inversion and the drilled out location. We did do Maxwell plate modeling. We got some modest or good conductors dipping to the northwest, consistent with the host geology dip, and slightly steeper. Okay, so we do have some ground data we can compare with. I've got, in the center, we have inversions, similar to what we did with the airborne VTEM data. We inverted the ground TEM data. Whoops, actually, I've got my labels mixed there, I'm sorry. So this is actually the VTEM inversion. This is the ground TEM. You can see it's a much less regular grid. We have much less coverage, but we did find a coincident line here in the ground data and here in the airborne. And the stacked profiles are shown. I see a very similar response from the two surveys. This is the Maxwell plate, which correlates very well with the 1D inversion. It's dipping slightly more steeply than what we see in the ground data. I think with the VTEM, we're getting an excellent correlation in the response. We're getting better resolution just because we're doing much, much more sampling. The ground magnetics, similarly, there's an excellent correlation between the airborne and ground, reduced to pole total mag. We're getting much better coverage. This data is a combination of the VTEM and ZTEM surveys to maximize the area that I can show. There's no simple answer, I think, regarding the specular hematite and magnetite zonation in the deposit. We should expect to see, I think, a relative high in the center of the deposit, according to that section, and it's really not present. There's certainly more definition in the ground data of faults, and there's an indication that the mag isn't directly telling us about the zonation of the minerals and about the lithology, but it's getting us into the right neighborhood. You can see there's a large mag high northwest of the deposit and no clear cutoff between that and the defined ore zone. I think that, the story is complicated by the remnant magnetization. It's complicated by having extremely high susceptibility and the potential for demagnetization in the magnetite. We don't really get to target the ore using the mag, but it gets us very close. I think the ground magnetics could have been quite useful. Perhaps that would have been a very useful immediate follow-up rather than DCIP. Whoops, I went back. Okay, and here's DCIP. This data was a bit hard to handle. I'm choosing to show some sections from the original report here, and I've geolocated. I've taken a section through the ZTEM inversion and compared it with the DCIP data. So on the top we have the conductivity from ZTEM. In the middle we have the resistivity from the DC resistivity survey. On the bottom we've got the chargeability. And we see a really good correlation there between the conductivity from ZTEM and the resistivity from the DCIP. We also see a good correlation in the area of the deposit with the chargeability and the resistivity. Unfortunately, the chargeability response is pretty much ubiquitous across the deposit. So I think, in the initial work, targeting holes based on the chargeability was maybe this was more of an excuse to drill in a location based on good prospecting information. It's really the conductivity and the resistivity data that's valuable from these surveys. Okay, so in conclusion, I think that this discovery was the result of acquiring a good ground in a prospective area to explore, doing a large regional survey, multi-parameter survey, good ground prospecting as follow-up. And really the story in terms of discovery in geophysics stops at that point. When we look sort of in a forensic way at previous or at subsequent geophysical work, I think we can say that the EM would have been a valuable tool to have access to earlier, and that if we're in a similar situation where we've got a relatively resistive host, something I didn't point out there actually, which is important, is that the host rock from the inversions, the host rock resistivity was something, or conductivity was something like 10 millisiemens per meter or lower, whereas the deposits were showing us something like under 150 millisiemens per meter. And that's pretty much the same as the conductivity we were getting from the alluvium. So really the deposits, as they become buried by the alluvium, disappear. We lose that valuable contrast in conductivity. So EM is useful in this situation where we have a relatively resistive host. In the alluvium, the value rapidly decreases. We'd have to have a much more conductive response to take advantage of the EM. In any case, I think the EM is valuable if you've got the right host rocks, you've got the right cover environment, you could rapidly accelerate location of these sorts of deposits. And I have some acknowledgements to Ed and Pascal, who did previous work on the project, to Giancarlo, who is with Capstone and did his MSc process on the project on this deposit. And if you want a thorough review, in addition to the 43 101s, you can get Giancarlo's thesis online, and to Brad Mercer at Capstone, who gave us permission to present this. And this is the only wildlife that I've seen in Chile, only substantial wildlife. That's one Akko on a hill. Anyway, that's
Thank you.
That's all from me.
Catch Francis later if you got some questions.